gonna record this. Okay, the record is now on, so we're back to this problem. Okay, now we have the moment equation. Okay, and right, this, remember, this is just for the actual case. We need to do this for the virtual as well. And I want to try to include this in the same page. So I'm gonna move this somewhere. Okay. Yeah. All right. So virtual now. Oops. If I decide to, keep my x at C, I would be rewarded by having easy equations for my virtual cases. Okay. So let's say I can say A, B, and B, C. Say for vertical deflection. Now my equation simply becomes minus x. Okay, my small m, and range is now from 0 to 10. And for my rotation, moment is easier. It's just minus 1. And the range is from 0 to 10 as well. It's a lot easier. But I sacrifice this moment equation so that I could get my hands on easier equations. Virtual. Okay. But I think best thing is to be flexible. Oh no, nobody told me, This is not W anymore, right? This is 2.5. We have the value for the uniform load. It's 2.5. Okay. So now we have the big M, we have the small m. It's time to assemble our equation. Okay. So let's say vertical deflection at not at B, at deflection, okay, at C. So let's call that delta C. It is integral from 0 to 5. The first one, that is minus 10x multiplied by minus x dx over ER. Plus the integral from 5 to 10 minus 10x, change that bracket, minus 10x minus 2.5 x minus 5 square over 2 multiplied by minus x. Again, run out of space. Move things in a bit. Oh, this 5 got separated. Okay, it's dx over 2er. And let's hope that if you can establish the integrals, the rest should be taken care of by your calculator. I hope you can perform this. Okay. If you don't, it's not a bad idea to train with one of your friends. You can grasp the use of the calculator. Okay. Just I never mean to measure your ability to perform this to the utmost level. You to be able to use a calculator to solve this is okay. Okay, so let's skip this and give you the number right away. I tried both integrals before and I got the same numbers. It must be correct. This is about 2043 over EI. And the final result is positive, meaning that the vertical deflection is in the same direction as the application of my virtual unit. Okay. Now is the delta C. Okay, it's essentially the same. Integral from 0 to 5 minus 10x, but this time I have to multiply this by minus 1 because it is the unit moment that we apply to get the rotation. Dx over EI plus integral from 5 to 10, same, minus 10x minus 2.5 over 2 x minus 5 squared multiplied by minus 1 dx over 2 EI. And the number is 339 over 9. It's actually 338.54 something, which should be 9. And again, the positive number here means the rotation is clockwise. Any question? And because we are going to have the on-site exam for the midterm number 2, the final should be the same, and we should stick to the date announced by the university for the final exam. Okay. Any question, folks? Okay. I think I'm gonna skip this one, and you can try to do it yourself, or we can come back to this if you want. The video clip may be available on the playlist because here it just this is nothing except the fact that you need to be careful with the range of the equation. That's all. I just want you to get into this frame thing to demonstrate how we can handle the frame. But you can guess if we can chop the beam into portions to take care of our integrals, just the same, just more portions. And because we talk about work, so you have to include the work of the entire system. That's all. Okay. And this problem demonstrates the fact that we have point load. So when you have point load, generally your integral is not constant. So probably we need to take care of the equation here, 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 and here. Here is 0, so probably no work anyway because there's no load. See? So even if we want to calculate vertical and horizontal displacement and rotation at A, where's A? Oh, that right? I hope there's no A. Well, no, where there's A, I think it's there. Okay? And even though you need to apply the load there at A, but keep in mind that no work is going to be done here because your actual load starts from the midpoint of that member. Correct? So there should not be any thing at all because zero moment there in the actual location. But that's well taken care of, I said. And, in order to do this, I think we need to give some names. So let's call this B and C and D and E. Okay, interesting again. The actual load case is like that. So let's, I think you have picture now that you need to write the moment equation for this load case. What about the virtual one? Like, not bad. Okay. So we got three identical structure to do the copy and paste option. So in order to get the vertical displacement, here we need to apply the vertical unit load. In order to have the horizontal displacement, we need to apply the horizontal unit load. In order to have the rotation, apply unit. So that's the case. This is not difficult. And of course, you need to perform your structural analysis, right? But when you have a unit load, it's kind of fun because it should allow you to see the equilibrium of things. So let me use the green. If this one is down, this one is up, correct? And that is a couple which creates the counterclockwise moment. So you need clockwise moment here. This is 7 meters apart, so that moment is 7. Simple as that. No need to sigma ME material. I actually say. For the second one, I'm going to quickly. Hope not. Should have to give time. For the second one, it's the same now. It's a horizontal load. So it's one there, so I have one here. And again, this is a couple counterclockwise, so I need clockwise moment here. And these two horizontal loads are 4 meters apart, so this moment is 4. Wow, pretty easy, right? Let's try to prevent our structure from rotating. The last one, I find it unbelievable that some students, when they face the pure movement, they cannot handle it. So if this is 1, what do we have? That is 1, right? That's it. Because you don't have the force. My moment here is not beautiful. Maybe I need to fix it. Okay. Okay. So now the fun is over. Time to write the moment equation again. Right? So yeah. We can actually assemble the maybe some sort of a table to include everything. So let's try that. So let's say this is big M. This is the let's say small m for delta B at A. This is small m for delta H at A. This is small m for rotation method. Okay. Okay. And again, I kind of like to start everything from the free end because it's easy. Even though you may argue that I can start from here, right? Guys, make notes. I think sometimes I'm beginning to feel like because you messed up because you can't find the better techniques to write the equation and equations. It's kind of sad because in the end, when you go out in the world, you don't really need to do this a lot. But I don't know. Sometimes this is like the basic functions of mathematics that you should also be able to master. Right? Back in my days, most students, if not all, who study engineering are good at math. How do you do that? Okay. So the impact test on iPad has been performed in the classroom. It's still okay, I suppose. All right. Where was I? Mathematics, right? Yeah. And now, in your time, I remember because I always ask in the class, do you like mathematics? Anyone who like mathematics in the class, please raise your hand. And it's like 4 or 5. Most students who study engineering now, they hate math. Yeah, they do. If you don't hate math, you will have the same feeling as I, used to have. What? Say some, and they struggle. And to my amazement too, that wow, you study engineering and you don't like. But thing is, they do like to study engineering, but they don't know what applies math. It's a bit of a shocking, but I'm used to it now. Oh, okay, this is the screen lock. So anyway, if you like math and you have good basic at math, this is really easy. So let's say portion AB. Oh, I'm going to break that into portion AB, B, C, and you know what? When I reach C, you're going to have to rotate the forces, right? So not very pleasant to change the angle of force. So when I reach that, instead of going through everything without any option in life, I prefer to work from this instead of trying to meet my demand at C and then move from C to D. It's very difficult. So I would sacrifice my my comfort of starting from the free end by starting from E, because C is not a free end anyway. E is not a free end. So to start from E would be easier than start from C, because I don't need to rotate my force. Correct? So let's call it ED, so that I start from E and then C. So that means I need to have my reactions here, right? So M gets the way. The reaction here should be 1 up, and 1 there. What about the moment? Now you have 2 couples actually, right? So your moment should take care of the moment. Your moment at the support should take care of the moment generated by these 2 couples. So the moment here should be equal to the horizontal force couple is they generate 2, right? And this generate another 2, so that is 4 unmetered, right? If you don't see this, just take sigma ME equal to 0, you see. Okay? So that means AB, come back to AB for the actual location. That's the most difficult one because you can't believe it's zero, right? But it is. Somewhere. Now, when you write the moment equation for BEC, this time don't forget that you need the node that is perpendicular to the member. So again, a little bit of a trigonometry. If that's the angle, that angle. And that is my favorite triangle, 3 and 4 and 5. So that's the one. 3, 4, 5. The side is 0.6. Oops, sine is 0.8, right? What's the sine? In 1 minute. Oh, because the angle of the cos is here. Right. So what's the angle? One second. No. That's the wrong angle because this is unusual. Okay, we need that. But this, if that's the angle, that is the angle, right? Yeah. So you need the sine, not the cosine. And when we reach BC, because again, I want to start the my virtual load from 0. So it BC, my x begins here. And when we use the sine is 0.8. This is 0.8, right? So at that location, I now have 0.8. But because my x begin from A, so here is x minus 2.5. Please be mindful that is a 3, 4, 5 triangle, so the true length of AC is 5 meters, right? If you're confused, I can maybe you can do it here. That's our diagram. That's 0.8, and our x begins here, and the entire length is of course 5 meters. Okay, so when we begin from there, this equation is applicable from x equal to 2.5 to 5, right? Right. So the range is, it's my range. My handwriting goes berserk already. It's my range. This is from 0 to 2.5. This from 2.5 to 5. So when I plug in x equal to 2.5, my moment equal to 0, which is correct. So that proves my equation here is correct. X equal to 2.5 make this 0. When I plug in x with 5, that should give me the moment at C. Okay? And ED. Now when we start from E, move there, my moment is going to be equal to -4 plus 1 multiplied by x, right? So, or I can just say x minus 4. And when I want to keep that x from E, when I reach D, my equation is x minus 4 minus that's 1, right? 1 in front, and then x minus 2. Correct? Minus sign will be at the same level. Maybe okay. I'll try. This is this. We have the moment equal to 4, and then you load is 1, so your x begins here. And then when you reach that unit load, when you x is over this, that has to be the load that got included. So when your x is beyond this point load, you have x minus 4 that comes from the support, and then here this term is going to have to be the load 1 minus this length, which is 2 meters. Okay, so we can wrap this up. Then this moment here, x minus 4 minus 1 multiplied by x minus 2. We can arrange this a little bit because x will be gone, and this turns out to be just a constant equal to -2. But you should know that this comes from that equation, so I keep it there. Okay. Let me move this a little bit up. Okay, so that maybe. And range, I've got the range. This is from 0. This is from 2 to 4. All right. Am I going too quickly? You guys are doing okay? All right. So this time we're gonna write the moment equation for small maybe. For vertical displacement at A. And now because I choose my origin like that, it becomes very easy. Okay, this is vertical load, so if that's the angle, that is the angle. No. I need the load. That's correct, right? That's the angle. So it's cosine, and it's a negative moment. So cosine is 0.6. So yeah, right here is point. Oops. That is minus. Oh, this should be minus as well. If the negative is minus. Okay. Minus 0.6x. And it continues to be the same equation, right? Minus 0.6x. And for ED, now we have this. So it is x minus 7. Right? Because we have the point load going up. So that is multiplied by x. So it goes up. if you write your moment equation from this goes up, it gives you positive moment, and this one comes down counterclockwise, so it's negative. So that's my x minus 7, and it's the same throughout the span because I choose to have the one origin for my x. We need the boundary. Very, very close. Maybe I can move my range to the right a little bit. And now the next one is moment due to for the horizontal displacement at A. Here is the horizontal load, just like that one, the actual load. So it's a sine, right? So that is minus 0.8. Guess now. So likewise, minus 0.8 x. And here, when you look at the support, you just have the moment, so it's just a constant, minus 4 and minus 4. Too fast? Can you see that? Without the free body diagram? Let's say, you know, when you look at things like this, when you look at structure, if you write the moment from left to right, anything that going to push your structure up to bend like that, that's positive, right? If you write the moment equation from left to right, and similarly, if you write from right to left, anything that will push your structure up, that's positive moment, right? Because that's your positive sign convention. Positive sign convention is like that. So I don't need to just go and clockwise, positive, clockwise, negative all the time. If you practice a little bit, you'll see this. It's just like that. You know, when you look at the right side of this, see that moment is pushing things down, so it's a negative moment. And this is the horizontal load that doesn't produce any moment. It's gone, right? When you write it here on the left side, see that one pushes your structure down, so it comes down like that. So it's a negative moment. It doesn't go up. Comes down, it's negative moment on either side. Goes up on positive moment on either side. Practice until you feel it. Don't memorize. Okay. And the last one is the moment for the rotation. Okay. This is constant, so it's very simple. Minus 1, minus 1, minus 1, and minus 1. So I think most of the time we would spend by dealing with right moment equation. After this, you just assemble them into the integral and let the calculator do the dirty work for you. So, let's say, I don't know if I could write everything before our time runs out. So let's begin. Delta V at A. Now this is this chunk, right? Because that's the moment when we apply the vertical unit load at A. So you multiply this together to get the virtual work corresponding to that. This becomes integral from 2.5 to 5. Okay. Minus 0.8 multiplied by x minus 2.5. This is multiplied by minus 0.6 x ex. Do we have constant EI? No, we don't. That's 1i, that's 2i, so be careful. Dx over EI. Okay. Plus the next integral is ED, so it's integral from 0 to 2, and it is x minus 4 multiplied by x minus 7 dx over 2 EI. Right? Be careful with the I. And then the last one is equal from 2 to 4 minus 2 x minus 7 dx over 2 EI. That sums up the work for the calculation of vertical displacement at A. You see, it becomes a little bit repetitive now. The concept remains the same. So, excuse me, for those of you who have the electronic device, you're going to be very comfortable because I think I'm just going to copy everything, right, to save some time. Okay. For those of you who prefer the lecture by hand, you have to put the hand. I don't know if you can do that. It's just too much. Oh yeah. All right. So let's pretend that we don't see that for the moment. The answer for this is 32.58 over EI. Positive means downward. But we are taking care of the next one. So please don't write anything. I'll wait for a minute because I'm just going to erase something here. You know. Okay. You guys at home, you ready? So now this time is going to be horizontal displacement at A, right? Which means I just get to change the function of the moment here. So instead of minus 0.6x, now I have minus 0.8. So this becomes minus 0.8 x. This change to a constant of minus 4. And the final answer is 28 over 33 over EI. It's positive, so that goes that way. The same way as our applied load. Okay. And the last one, again, we change function into minus 1. Right? Minus 1, minus 1, and minus 1. This is 7.5 over EI. Positive means that it is counterclockwise as the unit load. Because of the copy and paste power, finish in time. Any question? Wow. You know, I kind of like it this way that I can, you know, take time to see how students in the class doing, not going too quickly over things, because when this class was lectured online last year, I remember that I covered every example was on very quickly. In fact, every year when we have the class as usual on site or online, you know, it's impossible for me to cover every example. I just put as many examples as possible and see if I could cover it. And in online class, I could. It's gone very quickly. But now we have students very real life situation. We have one example left, and I'm pretty sure that we have a video clip available for this one. So you could try to do it yourself and see if you could match the solution on the video clip. It's like that. Okay. And now, is there any question? Okay. All right. So that is it for today. Please don't go. Let me talk about for a minute or two. So I'm just gonna stop the record first because there's no question, right?